Hello everybody, I'm Rich Corsi from the University of Texas at Austin. I'm chairing session 6, part 1 before lunch and part 2 after lunch. So we'll get right to it. Introducing our first speaker. Our first speaker is Richard Corsi from the University of Texas at Austin. So, thank you, Rich. Nice tie, by the way. So I'm going to speak about building science intersecting with science in buildings, or at least that's the title of my presentation. There's a subtitle involving robots. You have to follow me on Twitter. I'll tweet later about what that means. But I've been an advisor to Paula and the Sloan Foundation, the MoBE program, for about 7 or 8 years now. I've seen the program evolve. I've shown an image here of building science intersecting science and buildings, in this case microbiologists doing work in buildings. And I have to say the activation energy was really, really high to get building scientists, those who study buildings, together with microbiologists. And I don't think that connection, which has turned out to be a very fruitful connection, would have ever happened without a catalyst, and that catalyst was the Sloan Foundation. We wouldn't be here today without the vision of Paula and her colleagues at the Sloan Foundation. So thanks for lowering the activation energy, and I think this is a huge success. All right. So, some of you have seen me say this before, bear with me, but I'm not going to ask you what these numbers mean, I'll just tell you what they mean. Buildings are really important. The average American lives to be 79 years old. The average American spends 70 of their 79 years domiciled inside buildings. Spend 70 of our 79 years inside buildings. We spend more time, a greater fraction of our lives, inside buildings than whales spend submerged below the surface of the ocean. Think about that. Buildings are our ocean. We spend 50 of our 79 years in homes, 26 of our 79 years lying horizontally on a mattress with our face pressed up against a pillow, 5 years outdoors and 4 years in transit. So understanding microbes in buildings, I think, has great broader impacts. Definitely impacts the health of humans. We know that from hospital-acquired infections and lots of other things. Affects productivity, affects learning, but also affects the building. Rot affects structures, right? Biofilms growing on heat exchangers and HVAC systems affects the energy efficiency of buildings. So microbes do a lot to occupants as well as the structures of buildings. Buildings are also complex, right? So I think Jeff Siegel said yesterday, if you take a measurement of temperature and relative humidity in a living room and you call that the characterization of environmental conditions in a building, you're just wrong. In fact, you should never get federal funding again if you say that. Buildings are extremely dynamic. Changes occur in buildings on the order of seconds when HVAC systems cycle on and off, to decades in terms of oxidative aging and other types of aging of materials. They're heterogeneous, right? So if you just look at temperature on the plot up here, you know, you have temperatures in attics in the summertime in Austin. I measure this in my own house quite frequently, up to 60 degrees Celsius. And you have supply ducts running through the attics with air in them at 13 degrees Celsius. Across less than a millimeter thickness of HVAC duct, a huge gradient in temperature. And you see that all over the indoor environment. We see gradients in relative humidity, in illuminance, in daylighting, in materials, discontinuities in materials, in air speeds, in pressure across these spaces. And those pressure differences cause airflows that carry stuff from point A to point B. Daylighting's interesting. We get these steep gradients in space, but also in time, right? And if you've got a material that's in a lit zone with daylight, those materials can become very, very warm, especially if they're dark materials. This is a plot from our facade lab that shows a table near a window increase in surface temperature of 10 to 12 degrees higher than the background air temperature. So what does that do to microbes? I don't know, I'm not a microbiologist, but something to think about. Buildings are also deceiving. So I've done analyses of my own home. If I count the garage, the crawl space, the attic, and wall cavities, the unseen, or at least the unoccupied portion of my home is about the same volume as the occupied portion of my home. My entire home is about 50% unoccupied, right? So there's a lot of spaces in buildings that we don't think about because we don't see them. These unseen, occupied, hidden spaces, wall cavities, crawl spaces, attics. I have a colleague, Attila Novoselets, J.P. Maestro, who's here, I believe, Carrie Kinney, who are doing interesting work in portables, and they see these small pressure differences, minus 2 pascals to positive 2 pascals, and they can see the microbiome of the attic being injected into the occupied space or the crawl space in the occupied space under negative pressures, and then you reverse that with positive pressures with really, really small pressure gradients, right? HVAC systems are really understudied, in my opinion. There's lots going on in those systems, including heat exchangers that get up to temperatures of 95 degrees Celsius. So these are really extreme conditions in a building environment, and as low as 5 degrees Celsius. And then I'm not going to say anything about premise plumbing because I know that Amy's going to say that right after I speak. But the study of microbes in buildings, I think, has great intellectual merit just because of the complexity of buildings. Buildings are prone to human mistake, and this is following up on something that Richard said about schools being pig pens or something like that. I don't remember how he said it, but I do a lot of work with schools, some pro bono, some research in Central Texas, and I see these kinds of design features. See a lot of big external steel support beams with ceiling tile butted up right against them. There's 25 little humidifiers in every one of these classrooms that, eject a lot of moisture to the air. And when this beam gets cold, very conductive surface, when the outdoor temperature drops, you get a lot of condensation on that cold beam. And when you butt ceiling tile right up against it, you get wet ceiling tile. And every single school I've seen that has this design has exactly that. We have growth right here along the external beam. This is a school that has a downspout with a bunch of piles of leaves next to it and an air intake about 6 inches off the ground in this school. This school was closed for 2 years because of mold problems, and 2 teachers that went to the hospital with respiratory distress. Cost about $5 million to remediate this building. Here's a school that has a downspout that goes right into a drain that goes underneath the building. A colleague and I went underneath this building. It's a swamp down there, and the water was wicking up the walls, and this part of this building had to be closed and remediated. These are just dumb design features of buildings. And here you have an HVAC filter in a high school in Austin, right? Huge, thick cake on this HVAC filter. This white stuff is stuff growing on the filter, right? So very, very poor maintenance we see in high schools as well, in schools. Buildings are also prone to Mother Nature's wrath. We obviously have seen this recently. We're going to keep seeing it over and over and over again, and we're going to keep building buildings exactly the same as we always have, and we're going to keep seeing it over and over again. How do we deal with increasing intensity of storms that flood not tens of thousands of homes, but hundreds and hundreds of thousands of homes? Can we build and maintain buildings that are moisture resilient? At least from a building science perspective, this is a really important question. And how do we remediate, how do remediation efforts affect microbial communities? There's a cottage industry, maybe it's more than a cottage industry now, of companies that will come in after homes are flooded and remediate them. And one of the techniques they use for remediating is injecting really high concentrations of vaporized hydrogen peroxide, ozone, or chlorine dioxide into the homes. When I say high concentrations, I'm talking about hundreds of parts per million in the gas phase, not parts per billion, right? So really high concentrations of these compounds. What's the impact of injecting these chemicals in terms of material susceptibility to fungi? So we have a little bit of evidence through some research we're doing at the University of Texas that when you ozonate bamboo at really high concentrations, it becomes much easier to grow mold onto bamboo. But that's like one data point. How does the returning microbiome after remediation change? How do reaction products impact microbes? So my team's done a lot of work with these 3 decon agents, and we expose 24 different materials to these decon agents. We do a lot of replicates as well. And we look at what's formed when you hit materials with decontamination agents. All right? This is total building disinfection byproducts. So this is a sum of everything we see for a 24-hour period after a 12-hour exposure. All right? We also speciate this sum, so we know what all the chemicals are associated with these bars. We see a lot of aldehydes, a lot of carbon ketones, so carbonyls, carboxylic acids. With chlorine dioxide, we also see a lot of haloketones, and they're the same kinds of things you see when you disinfect water with chlorine dioxide. So we're seeing chlorinated propanone, for example. We also see evidence of corrosion on metal materials when we inject chlorine dioxide into buildings. We put copper-coated slides in our chambers when we do these experiments. We can see corrosion of the copper-coated slides. So there's a lot going on in the building when you inject these chemicals at really high concentrations to try to remediate the building. Something to think about for the future. Building materials also transform dust. We tend to think of materials as substrates, right? Things grow on materials. Materials also transform things that deposit on them. Many materials contain semi-volatile organic compounds, plasticizers, flame retardants, perhaps some fungicides. And those materials are emitted very, very slowly from the material. And next to any material that contains these SVOCs, there's going to be a very thin boundary layer, about the thickness of a skin of an apple, but certainly greater than the diameter of most particles that deposit on them. And so you have very high concentrations of SVOCs in the gas phase right above the surface. Any particles that deposit on the surface can have these SVOCs partition into them, especially the organic phase of the particles. So imagine that there's bacteria and fungal spores, et cetera, that are part of that dust, which we know happens. What happens to them in that rich SVOC environment? Right? So a colleague of mine, Ing Zhu, has been doing some research in the University of Texas test house, which is a 1,200 square foot, 3-bedroom, 2-bath test house. And the floor of the test house, by Ing's group, has characterized the composition of so many of the materials in our test house. It's the most characterized, I think, house in the country. But the floor is the only place where you find butyl-benzyl phthalate. It's used as a plasticizer on the floor. It's something like 20% of the floor mass. It's a huge fraction, but that's very common, actually. So when Ing's group, her students, collect floor dust and then dust from all the other surfaces inside the test house, these are the kinds of results you see. This is butyl-benzyl phthalate concentration in dust in micrograms per gram. So for the floor dust, we're up in the order of 2.5 milligrams per gram. That's a really high concentration of butyl-benzyl phthalate, right? This plasticizer in floor dust. And we know that there's microbes that are wrapped up in that floor dust, as Jessica spoke about yesterday, all right? So what does the butyl-benzyl phthalate, or any of these kinds of compounds that we see emitted from indoor materials, do to the microbiome of dust? I think that's a really interesting question that hasn't really been probed by anybody. Building a research future. So this is my slide from a building science perspective. This isn't a new journal, building science perspectives. This is from a building scientist perspective, what kinds of research would I like to see done involving microbiologists, right? So one is to do more to study unoccupied spaces in buildings and the connections between the unoccupied spaces and the occupied space. I think a much deeper analysis of HVAC systems where you can have spot condensation in supply ducts, you have these extreme temperatures on heat exchangers, you have biofilms growing on heat exchangers. I know that there's been some great research that's been done in the past. Bill Bonfles has done work on biofilms, Jordan Pecci, and I think Jeff Siegel are doing some work in that area right now. So that's really promising, but I think we need more work in that area. I think more research on remediation effectiveness. Carl Grimes asked yesterday, when do we know we're done remediating a facility, a building? So that's a good question, right? And also, what happens to the microbiome after we remediate? Especially the microbiome that grows back in the building. Is it different than the one that existed before we remediated? More research on material characteristics. We know so little about the physical and chemical properties of materials in buildings. The morphology, the composition, the porosity, and so on and so forth. And interactions with fungi and how those characteristics affect fungi and materials. Material transformations. I would like to see us think over the next 10 years about how we transform the interiors of buildings to make materials work for us instead of materials always being the enemy that things grow on. Obviously, everything we do is related to health outcomes, almost everything we do. And I think as we move forward into the health arena, I hope that we keep in mind not just the microbes that might be causing health effects, but the building factors that are affecting the microbes that might be causing health effects. The National Academies report that I think Joan Bennett will be talking about in a little bit actually has some additional recommendations in it, including building science recommendations, and I encourage you to read that. Right? So I think ultimately the question is how do we design, construct, operate, and maintain buildings with microbial communities in mind? And as a building scientist, that's what I hope we do. All right, so a few acknowledgments. I've already acknowledged Paula and the Sloan Foundation. None of this would have been possible, everything that everybody's talking about today, without the stimulation and the lowering of the activation energy needed to get microbiologists and building scientists working together. Several UT colleagues are listed here that were responsible for some of the slides that you saw, or at least bits of parts of slides. And then Jeff Siegel, who's here today. Jeff is an ex-colleague at the University of Texas, and Jeff and I have always thrown ideas off of each other, and in prepping for this presentation, I called Jeff on the phone in Toronto and sort of threw some ideas off of him, and he gave me feedback. That's an interesting photo from 2005, and it also stimulates me to recommend that maybe we do microbiomes of the hair environment, something like that. So Jeff would be a good subject for that. One or two questions? All right, one or two questions? Remember, I'm a building scientist. I have not had biology since high school. So I'm trying to absorb as much as I can from microbiologists.
So I'm not a building scientist, I'm a microbiologist. So if someone has a home and they want to put a new addition on or new piping in, on the material side, can we make recommendations on choices? They're redoing their bathrooms, say. What do you think they should be?
Yeah, so I think, bathrooms, anything that can have water removed quickly, that can be squeegeed, or whatever they call those things that you use in your shower, right? Get rid of moisture, make sure you have a proper fan in the bathroom. I'm focusing on bathrooms because you mentioned bathrooms. Moisture-resilient materials are better than those that retain water for long periods of time. So, Jeff said to me yesterday, he said it's all about water. If we have available water, stuff will grow, and I think that's true. And that's the starting point for studying these things. I think the floods we're seeing in the Gulf Coast right now, all over the country. And by the way, the image I showed of a tented house that was being fumigated with chlorine dioxide, that was Syracuse, New York. So it's not just the Gulf Coast, it's all over the country now, this stuff's being done. I think that's where the action is. We're talking about hundreds of thousands or millions of people being affected probably every year for a long period of time. And those are sort of the worst case, extreme case, the extreme examples that we should focus on is how do we build moisture-resilient homes in those areas. Okay, so our next speaker is Amy Pruden from Virginia Tech University, and she's going to tell you about one of those hidden spaces in buildings that we often don't think about, which is premise plumbing.